In this video, we are going to discuss Gauss divergence theorem. The problem given here is verify Gauss divergence theorem for f vector is equal to x cube I vector plus y cube j vector plus z cube k vector taken over the cube bounded by x is equal to 0, x is equal to a, y is equal to 0, y equal to a, and z is equal to 0, z is equal to a. What is given in the question? We are given a vector f vector that is equal to x cube I vector plus y cube j vector plus z cube k vector. And we are given a cube bounded by the surfaces x is equal to 0, x is equal to a, y is equal to 0, y is equal to a, z is equal to 0 and z is equal to a. We are going to verify Gauss divergence theorem. What is the statement of Gauss divergence theorem? Double integral over S f vector dot n vector ds is equal to triple integral over v del dot f vector dv. Let us recall what is del vector. Del is equal to dou I vector by dou x plus dou j vector by dou y plus dou k vector divided by dou z. Here we take the given f vector as f1 I vector plus f2 j vector plus f3 k vector. Then what is del dot f vector? We multiply ith component together. We get dou f1 by dou x plus we multiply jth component together. Dou f2 by dou y plus we multiply kth component together. Dou f3 by dou z. What is dv? dv is dx dy dz. Let's start from the given f vector value. Our right hand side is triple integral over v del dot f vector dv. That is equal to, we replace del dot f vector value and dv value. From f vector, what is f1? f1 is x cube, f2 is y cube and f3 is z cube. We replace in the right hand side dou f1 by dou x, differentiation of f1 with respect to x. What do we get? 3x square plus differentiation of f2 with respect to y, 3y square. Next, dou f3 by dou z, differentiation of f3 with respect to z. We get 3z square. We keep dx dy dz as it is. Here we are given the limits x varies from 0 to a, y varies from 0 to a and z varies from 0 to a. Now we are integrating this one. What is the integral of x square? That is x power 3 by 3 plus 3y square is a constant. So when integrating dx we get x plus 3z square constant. When integrating dx we get x. Limit varies from 0 to a. We replace the upper limit a and lower limit 0 in the place of x. Now we are going to integrate with respect to y. A cube is a constant. So when integrating dy we get y. 3a is the constant. Integration of y square is y cube by 3 plus 3z square a constant term. When integrating dy we get y. Now we replace the upper limit a in the place of y minus lower limit 0 in the place of y. Now we are going to integrate this with respect to z. A power 4 is a constant. So when integrating dz we get z. Plus again in the second term a power 4 is constant. Integration of dz is z. Plus 3a square constant term. Integration of z square is z cube by 3. We are replacing the upper limit a in the place of z minus lower limit 0 in the place of z. We eliminate this one. We get 3a power 5. So that the right hand side value is 3a power 5. Let us find the left hand side now. For this we calculate integral over s f vector dot n vector ds over all 6 faces of the cube. Consider the cube as shown in the figure. The first surface S1 is GEDA. Here what is the normal to this surface? The outward normal is along the positive direction of x-axis. So that n vector is equal to I vector. What is ds here? So on this surface we have x is equal to a, so that our dx becomes 0. We have y and z coordinate alone, so that our ds is dy dz. You consider the next surface OBFC. Here what is the normal to the surface? Negative direction of x-axis. So that we take that as minus I vector. Equation of the surface is x is equal to 0. So dx value becomes 0. We have y and z coordinates alone. So ds is equal to dy dz. Now consider the surface BFDE. Here the normal vector is positive direction of y-axis. So that is j vector. Equation of this surface is y is equal to a. So dy value becomes 0. We have x and z coordinate alone. So ds is equal to dx dz. On the surface OCGA, the normal is negative direction of y-axis. So we get minus j vector. As y is equal to 0, our dy value is equal to 0. We have x and z coordinate alone. So ds is equal to dx dz. On the surface GEFC, the n vector is positive direction of z-axis. So we have k vector. Here z is equal to a. So dz becomes 0. We have x and y coordinates alone. So our ds is dx dy. Last surface OADB. The normal vector is negative direction of z-axis. That is minus k vector. Here z is equal to 0. So we get dz is equal to 0. We have x and y coordinates alone. So ds is equal to dx dy. Let's start from the first surface. Double integral over r f vector dot n vector ds is equal to, we replace double integral f vector value dot the corresponding n vector value, that is I vector. Here ds is dy dz. We apply dot product. So we multiply ith component together. We have x cube dy dz. What is x value on this surface? X is equal to a. So we have a cube. A cube is a constant. Now we are integrating with respect to y. So integral of dy is y. Limit varies from 0 to a. We are applying the limit in the place of y. Upper limit value minus lower limit value. We get a power 4. Now the integration is with respect to z. A power 4 is a constant. Integral of dz is z. We replace the upper limit a and lower limit 0 in the place of z. So value on the first surface is a power 5. Now let us consider the second surface. Here the outward normal is minus I vector. We start from the definition. We substitute f vector value and n vector value and ds value. Here the limits are y varies from 0 to a and z varies from 0 to a. We apply dot product. For this we multiply ith component together. We get minus x cube. The remaining term becomes 0. Here what is x value? X is equal to 0. We replace that. We get the integral value as 0. Now let us consider the third surface. Here the normal is j vector. The integral value is equal to double integral. We replace f vector value dot n vector value ds value. Here the limit of x varies from 0 to a. Limit of z varies from 0 to a. We apply dot product. So we multiply the jth component together. We get y cube. The remaining term becomes 0. What is y value here? Y is equal to a. So we get a cube. Now we are integrating this with respect to x. A cube is a constant. Integral of dx is x. We replace the upper limit and lower limit in the place of x. What do we get? We get a power 4. Now we are going to integrate this with respect to z. A power 4 is a constant. What is the integral of dz? That is z. Now we replace the upper limit and lower limit in the place of z. Eliminate. We get a power 5. So the third surface value is a power 5. Now we consider the fourth surface. Here the normal is minus j vector. We start from the definition. Substitute f vector value dot n vector value ds value. We apply dot product. For that we multiply jth component together. Remaining term gets 0. What's the value we are getting? Minus y cube. What is y value here? Y is equal to 0. So that the integral value becomes 0. Fourth surface value is 0. Now we consider the fifth surface. What is the normal vector here? K vector. Start from the definition. Substitute f vector value, n vector value, ds value. Apply dot product. We multiply kth component together. Remaining term gets 0. So we have z cube. What is z value here? Z is equal to a. So what do we get? A cube. A cube is a constant. Now we are integrating with respect to x. What is the integral of dx? Integral of dx is equal to x. Replace the upper limit and lower limit in the place of x. What do we get? We get a power 4. A power 4 is a constant. What is the integral of dy? Integral of dy is y. Replace the upper limit and lower limit in the place of y. Now what do we get? We get a power 5. So that the fifth integral value is a power 5. Now let's start from the sixth surface. The normal to this surface is minus k vector. Start from the definition. Substitute f vector value, n vector value, ds value. Here the limit of x varies from 0 to a and y varies from 0 to a. Now we apply dot product. We multiply kth component together. Remaining term becomes 0. What do we get? Minus z cube. What is the value of z in this surface? Z is equal to 0. When we substitute, the full integral value becomes 0. So that the sixth integral value is 0. So we start from the left hand side of the definition. That is equal to sum of all these 6 values. When adding, we get 3a power 5. So that the left hand side value is 3a power 5. As the left hand side value is equal to right hand side, Gauss divergence theorem is verified. Let us summarize. We first find del dot f vector value. Then we find the right hand side. Right hand side is equal to triple integral over v del dot f vector dv. We find n vector and ds for all 6 surfaces given. Then we find double integral over s f vector dot n vector ds for all 6 surfaces given. The left hand side is equal to double integral over s f vector dot n vector ds is equal to sum of all 6 surfaces values of double integral over s f vector dot n vector ds. Finally, we found left hand side is equal to right hand side. The Gauss divergence theorem is verified.